All right, here are the solutions to the recitation problems from Wednesday, April 15th. These questions are about moment of inertia getting set up to do rotational motion. So problem one, we're asked to find the moment of inertia of the rod shown below around the axis indicated. There are two different ways that you could do this. One of them would be to think of this as, so we have a formula for the moment of inertia of a rod about its end. And one way to do it would be to think about the moment of inertia of this piece, think about the moment of inertia of that piece, and then add them together. Another part would be to use, or another way would be to use the parallel axis theorem. And that's what I'm going to do here. So the parallel axis theorem says, I'll write it up here, says that the moment of inertia around any point is equal to the moment of inertia around the center of mass plus m d squared, where d is the distance that the axis is shifted. So in this case, for a rod around its center, its moment of inertia is not 1/2, is 1/3, actually, is 1/12 ml squared. But the distance it has been shifted is 1/3 L. So this shift amount here is 1/3 L. So the total moment of inertia is 1/12. Come on. 1/12 ml squared plus, for this piece, m times that amount squared. Uh, 1/3 L squared. So that gives me 1/12 plus 1/9, which is, write this in green, come on, pen. So let's see, 1/12, I need a common denominator, that's 3/36. 1/3 is, 1/3 squared is 1/9. 1/9 is 4/36. So that's going to be 7/36 ml squared. Problem 1b. What is the moment of inertia of a sphere of mass m and radius r rotating about a point on its surface? This is again the parallel axis theorem. So I can write that the moment of inertia of a sphere around the edge is, so it's the moment of inertia of a sphere around its center plus, in this case, we're shifting the axis by the entire distance. Here we shifted the axis only by 1/3 of the length, but here we're shifting it by r. So this is just going to be mr squared. And This term is 2/5 mr squared. That you would have to look up in a table. I don't expect you all to remember that. I only know that because I've been teaching this class a lot. So that means that the moment of inertia of a sphere about its edge is equal to 2/5 mr squared plus another mr squared, which is 7/5 mr squared. Uh, 1c, what is the moment of inertia of a circular plate of mass m, radius r, and thickness d rotating about a point on its edge? So, same deal. Moment of inertia of a disk about its edge is equal to the moment of inertia of a disk around its center, again, plus 1/2, plus the term that comes from the parallel axis theorem. Sorry about the clicking noises. I'm being sent Slack messages. This distance is r. It turns out that the thickness d doesn't matter. So this term here on the left is going to be 1/2 mr squared plus another mr squared from the parallel axis theorem is 3/2 mr squared. So all of these problems are the same, really. A is actually the most complicated, in that you had to think hard about how far you have displaced the axis. You displaced it 1/3 of the length. And in the others, you've just displaced it by the radius r. So in part 2, we are thinking about conservation of energy as this thing falls. So I'm just going to go through all of the parts. There are lots of them. Okay, part A. What is the moment of inertia of the system in terms of m and l? So I know here that the moment of inertia is not 1/2, I miswrote, 1/3. I need my smaller pen for this. I equals 1/3 ml squared. Again, this is something you would need to look up in a table. Oh, yeah, the rod, I'm sorry. I am completely misguided here. I didn't read the problem. I forgot that the rod is massless compared to the ball. That's important. So in this case, if the ball is the only thing whose moment of inertia matters, it's a distance L away. And for a point mass, the moment of inertia is just mass times the distance from the pivot squared. Okay, we're releasing it from rest. So the initial kinetic energy then is 0. The final kinetic energy is going to be 1/2 I omega final squared, which is 1/2 m L squared omega final squared. So for the initial and final potential energies, so I will choose this line as y equals 0. And then this line, where the little ball starts, this will be y equals L if that is y equals 0. I can choose any axis I want. So in this case, the initial potential energy is just mgl, because I'm L above baseline. Final potential energy is 0. Why is the energy of the ball conserved? This is an interesting question. There are kind of some subtle answers to this, but all of them come back to the point that the only external force on this system comes from the normal force of the pivot, right? We've nailed this thing into a wall, and the only external force happens at the location of the pivot. But since that's not moving, it can't do any work. There are ways of using different mathematics to say that, but that's the upshot. So energy of the ball is conserved. There are no actually, there is another external force, but that's gravity, and we associate that with the potential energy. So the force of gravity, we are accounting for its work through gravitational potential energy, but the pivot does no work since it doesn't move. So that's maybe a long-winded answer, but that's what it is. Write down energy conservation using the values you derived. Okay, so I have my initial potential energy, so mgl. Well, we'll write this down in words first. So the potential energy at the beginning is going to the final kinetic energy. So we've got mgl equals 1/2. Whoops, I went from uppercase to lowercase m. I guess the problem says I should be using uppercase m, right? So uppercase mgl equals 1/2 ml squared omega final squared. I can cancel the mass, so I don't need to worry about whether it's uppercase or not. I can cancel 1L from both sides. I'm supposed to find the final angular velocity. So omega final is, well, that's just going to be the square root of 2GL. Now, we could kind of expect this because this is what you would get if you just dropped a ball from some height. And we saw previously that the result of like dropping a ball from some height gives you a final, wait. Oh, no, that's 2G over L. That's important. Yeah, because 2G over L, the meters will cancel, the units do come out right. The thing that's worth noting about this is that here, this gives us a final velocity of square root 2GL. And that's what you'd get if you just rolled a ball down a ramp, or slid a ball down a ramp, rather. So this result shouldn't surprise us. Question 3 now asks you to think about a situation where you have both rotation and translation going on. So as this thing falls, it moves that way, but it also rotates that way. So if I am sketching this at the initial position, then it's going to be looking like this. All right, here it is. Here's this thing just hanging there. I'll draw it shorter just so we have something more interesting to draw. And then after it has fallen, it's going to be down here. It'll be hanging from this string. This height here is h, and its center of mass will be moving down at some velocity, and it will be rotating at some angular velocity. I'm going to set this position up here. Actually, let me draw this in a color that shows up better. Well, we'll call the final height 0 and the initial height h. So I guess the height that it falls, then we should label like that. So we'll call this y equals 0, this y equals h. So the initial kinetic energy is 0. Gravitational potential energy, well, before it is mgh. After it is 0. The final kinetic energy is a sum of two contributions, one from the linear motion of the center of mass and one from rotation about the center of mass. Express the final linear kinetic energy in terms of m and vf. So I don't have much room to write here, but I'm going to do this in blue, and I may wind up switching colors. So here, the kinetic energy final is the translational kinetic energy plus the rotational kinetic energy, which I want to write in a different color. We'll do that one in orange. So translational kinetic energy is just 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. Okay. So the next couple of parts I'm going to kind of do all at once. So this was Professor Rudolph's problem, and I didn't write the parts like this, so I'm having to think about them. So D, E, and F I'm going to think about all at once. So part D is just asking you to find the translational kinetic energy, 1/2 mv squared. The moment of inertia here, well, the moment of inertia of a rotating spool, a cylinder of radius r, is 1/2 mr squared. And so that means that substituting that in, the final kinetic energy, I've got the translational piece, 1/2 mv squared, plus the rotational piece. Now I can substitute this in. I have 1/2 times 1/2 mr squared omega squared. But heading down to part G, note that if since this thing rolls without slipping, I have the no slip condition, which tells me that V equals omega r. So And this is a big deal. So everybody watching this video, this pattern that you're about to see comes up again and again and again. Notice that I have r squared omega squared here. The r comes from the moment of inertia. The omega comes from the formula for rotational kinetic energy, 1/2 I omega squared. So this is just v squared. That substitution happens very often in these problems. So putting everything together, I have the initial potential energy equals the final kinetic energy, which is translation plus rotation. And that's going to be 1/2 mv final squared plus, I'm not using final here because that's the only velocity, plus the rotational part, which is 1/4 mv squared. So where did that come from? The 1/4 came from 1/2 times 1/2. The mv squared came from the fact that r squared omega squared is v squared. You will see this pattern again and again and again. So that means that, oops, mgh equals 1/2 plus 1/4 is 3/4 mv squared. So v equals the square root of 4/3 gh. This is a classic problem. We will see this problem again and approach it from a different way. So let's talk about what we did. We saw that we know the gravitational potential energy and we know it's being converted into kinetic energy. But that kinetic energy takes two forms, rotational kinetic energy and translational kinetic energy. So when we write down the formula for the final kinetic energy, right, we have to include both, the translational plus the rotational parts, right here. And then, so we notice one of them has v's and one of them has omegas in it. So when we put in the moment of inertia, we have this expression. So here is the translational part. Here is the rotational part. And then we observe, but this thing rolls down without slipping. So I can make the substitution and observe that this r squared omega squared that appears there, that's just v squared. And then making that substitution simplifies everything greatly, and that term gets plugged in here for the rotational kinetic energy. So thank you all. If you have any questions after watching this video, please send me an email or ask me a question on Discord.